Today I'm going to talk about problems that deal with the motion of two vehicles, and we'll deal with vehicles that will move towards each other or away from each other. This is not a complex, physics type problem. This is just going to be a basic algebra problem that deals with linear motion that's constant and there's no acceleration going on. So just to kind of help understand where the formula is coming from, I want to start by just assuming we have a car. And let's say that our car collides with a tree, okay? And let's say that our car is going 45 miles per hour, okay? When it hits that tree, we're going to call that a 45 mile per hour collision. So, that would be kind of a bummer to bump into that tree. Now, assume now that we have a car that is heading towards another car. So both vehicles are now moving. And the first car is going 45 miles per hour, and the second car, we'll say, is also going 45 miles per hour. So let's assume these two cars are going towards each other, and then they're going to collide, somewhere in the middle. This collision, and why this is so dangerous, is because if you have two cars that are heading towards each other, you would add the speeds to find the speed of collision. So in this case, that would actually function like a 90 mile an hour collision. So even though these cars are going, at a speed that is probably slower than some highway speed limits, if they collide into each other, it's such a dangerous collision because it's a 90 mile an hour collision. You add the two speeds together. Likewise, if you ever see somebody get rear-ended, or if you've been in a car that's been rear-ended before by another car, if you have two cars going a certain direction, let's say this one's going 45 still, and then let's call this one, let's say it's going 30 miles an hour. Okay, so if this car, this 45 mile an hour car, bumps into this car from behind here, we're going to actually subtract the speeds because this car is going to help take some of that 45 mile an hour motion away, whereas in the tree wasn't moving, the tree got hit harder. If this car is moving in the same direction as the car that's chasing it, we're going to subtract the speeds because relative to each other, this one's only going 15 miles an hour faster. So this is probably the least severe collision as far as things go. So why did I go through all that? This is to help you remember something in this two-vehicle motion formula that I'm going to use, which is RT, or the rate times the time, plus, and I'm going to put a minus down here too, the rate times the time equals the distance. And again, same thing here. I'm going to sneak a little minus sign down here. I'll show you why in a second. This formula is going to work for, so normally you'll add. So if the things are going opposite directions, you're going to add the speeds. For the same reason that when these two things were colliding, and actually if they were going away from each other, so if two things are going towards each other or away from each other, then relative to each other, they're moving faster. So we have to add the speeds together. Now, when this formula will change is if things are going in the same direction. So if they're going in the same direction, we just want to make that plus sign into a minus sign. So we're going to subtract. And when I say same direction, I just mean that two objects are chasing one another. One is going after the other one. Okay, and if that's the scenario, we're going to subtract. One helpful thing is that if you're missing the distance in these formulas, those are the tricky examples. Don't forget that the distance equals rate times time formula can sometimes help you find the missing distance. So the rate times the time of the one vehicle, so we'll call this vehicle 1, is equal to the rate times the time, plus the rate times the time of the second vehicle. We'll call this vehicle 2. Is equal to our distance, or the distance that they are apart, or the distance that, how long it takes them to get to a certain distance apart. Let's look at a problem here. So, while driving in the desert, James Bond discovers a bomb in his car that is about to explode. He puts the car in cruise control and jumps out of the car and immediately begins running the opposite direction at a speed of 15 miles per hour. If the car's cruise control is set to 50 miles per hour and the bomb's blast radius is 1.08 miles, how long will it take Bond to escape the bomb's blast? Round your answer to the nearest minute. Okay? So what we're going to do here is look at how long it's going to take for Bond to get to safety. All right, so if he sees that kind of time ticking down on the bomb, he knows, okay, I have enough time to escape or I don't. He probably wouldn't be doing this math in his head. Now, physically, this is impossible to jump out of a car and go completely the opposite direction at 15 miles per hour at a constant speed. But again, just bear with me here. I know physics people might have a problem with this, but for the sake of algebra, we're trying to just look at a two-vehicle motion problem. So we've got a car going this way. And we've got James Bond, who's jumped out of the car, and he is running for his life here. This is the best I've got. I know I'm no artist here, and he's going this way. So he's going 15 miles per hour. And our car here is going 50 miles per hour. Okay, so they're running opposite directions, and we're trying to get them far enough apart so that when they get, 1.08 miles apart, they'll be safe. Sometimes for these problems it helps to set up a chart, and the way that I'll set these up is by labeling the two things we're talking about. So make a little mini chart here. Okay, and what I'm going to do is put rate and time, so a little rate times time chart. In the first column of the chart, it just helps to put the two things you're talking about. In this case, we're talking about Bond, and we're talking about the car. So we know that Bond's rate is he's running at 15 miles per hour, and the car is going 50 miles per hour. So that's easy to fill in right there. So the rates shouldn't be a problem. And the time, if you look carefully, it says how long will it take Bond to escape the bomb's blast. We don't know the time, so we could either fill in an X here. I'll fill in a T. It doesn't really matter what variable you use, so I'll fill in a T here. And then what I'm going to do is now plug the R and T into that equation. That distance is equal to the rate times the time of the one vehicle, and then we'll decide if it's plus or minus here in a second. Plus or minus, we're not sure which one, the rate or the time of the second vehicle. All right. Now, if we look carefully at this problem, since Bond and the car are going in opposite directions, we need to add. If they were chasing one another, we would subtract. If Bond was running after a runaway car, or if the car was chasing after Bond. So we're going to have to add in this case, not subtract. So to set this up, we've got 15t plus 50t, so the rate times the time plus the rate times the time is equal to the distance, and we're looking for that distance, which is 1.08 miles that they are apart. Okay, so from there, we're going to have to combine our like terms. We've got our 15t and our 50t will give us 65t. And from there, we'll have to go ahead and divide 1.08. So 1.08 divided by 65, and I'm coming up with about 0.0166 for our time. Now, currently, since this is in miles per hour, we're currently in hours, but if you look carefully here, they want us to round our answer to the nearest minute. So we're looking for a time measured in minutes. All right, to do that, we're just going to have to take our answer and multiply it by 60. Okay, so that'll convert it into minutes for us. So if I take my answer and I multiply by 60, I'm coming up with 0.9969 or so minutes. Which, if we're rounding that to the nearest minute, well, guess what? He's got about 1 minute to get away before, he's got about 1 minute until he's back to safety. So if the bomb has 60 seconds on the clock, he's still okay. If it's got less than that, he's going to be in a little bit of trouble. All right, so that's a first example. Next one. Joaquin begins jogging at a constant pace of 5 miles per hour directly north from a campsite. 2 hours later, Sally jogs north from a campsite at a rate of 8 miles per hour. How long will it take Sally to catch Joaquin? All right, once again, we're going to have to look at our formula. And we'll have to decide whether we're adding or subtracting. Now, in this case, since Sally is chasing after Joaquin, it's going to be a subtraction problem. So we're dealing with the variation where we're going to subtract the two speeds. Okay. This will be for our first vehicle. This will be for our second vehicle. We use vehicles loosely here. Our vehicles will be people in this case, but that's okay. So I'm going to set up my chart here. we've got our rate and our time. We've got Joaquin and Sally. And if we look here, the rate of Joaquin was 5. We're looking for how long it's going to take Sally to catch Joaquin. So that's going to be X or T. I'll use X in this example, just 'cause sometimes my T's look like plus signs. And then Sally would be going 8 miles per hour. And once again, we're looking for the time that they meet up, and that should be the same for both, so that would be X. Now, we're looking at our rate times our time. A helpful thing in this case would be usually put the faster person in these problems first. Otherwise, you're going to get a negative answer, which doesn't make a whole lot of sense. You could do it the other way as long as you make your answer positive. But just to avoid that, we're going to put the faster person first when we subtract them. So I'll take 8x minus 5x is equal to... Wait a second. So we're missing something here. So I don't see a distance in this problem if we look through here carefully. Sorry if you can hear the train beeping in the background. So now that we've got our 8x minus 5x, we need to find out the distance. And the distance that we want here is, if we've got Joaquin with this big head start, we want to find out how far had Joaquin gone just as Sally is deciding to leave. Wow, that is a really bad drawing. She looks like she's about to trip. But anyway, you get the idea. So if this is Sally, we need to find out how far apart they are just before Joaquin leaves. Or excuse me, just before Sally leaves. Now to do that, remember that Joaquin begins jogging at a rate of 5 miles per hour from a campsite, and he's got a 2-hour head start. So we can actually calculate how far this distance is using our distance equals rate times time formula. Well, Joaquin traveled for 5 miles per hour for a time of 2 hours. Okay? This can tell us how much of a head start Joaquin has. So in this case, if we multiply here, that would be 10. So that would be our distance. So 5 times 2 gives us that, if I travel 5 miles an hour for 2 hours, I've gone 10 miles. So this distance here between them is 10 miles. So all we have to do now is solve. So if we subtract here, we get 8x minus 5x, which is 3x. And then if we divide by 3 on both sides, this should tell us that x is equal to 3 1/3 hours. Or if you want to use minutes, that'd be the same as 3 hours and 20 minutes. Okay, but 3 1/3 hours will be fine for this example. They must be marathon runners if they can run at a constant speed for that long. I'd probably be falling apart with rickety old knees. But that's how you solve these problems. Again, if they're moving the same direction, one person's chasing the other, we subtract. If they're moving opposite directions, meaning towards each other or away from each other, we add because their speeds are faster relative to each other. Okay, they move apart or towards each other at a faster rate. We use that distance equals rate times time plus the rate times time of the other vehicle minus again in the other instance, and you can't forget distance equals rate times time for some of the problems that don't give you the distance.